So apart from these different topologies, there is another consideration: how many poles we should have, because this is something again drives the design. So we are, you see, in throughout these whatever we were discussing, it's all trade-off study. What we are trading off, it's nothing is too good, nothing is too bad. So it's ultimately it's our call where to trade off and which technology we should consider for further. So you will see Tesla is using some other technology, or some BMW is using some other technology, but there is where the trade-off is coming from. So where you trade off actually. So this is another area: 6 pole, 8 pole. There are a lot of debates on 10 pole versus 6 pole versus 8 pole. And mostly you will see many times a machine will be either 6 pole, 8 pole, or a 10 pole, because they fall in a very say sweet spot, or say a golden mean area where the switching frequencies, the size of the machine, and you see the size of the machine or the OD of the machine shrinks as I increase the poles. So you see this is a flux return path where you don't need so much of steel on the outer, because the conduction is on only the smaller part of portion of it. So these are all the trade-off that we have to ultimately make. Say I can say design choices that we have to make. IPM, I'm considering IPM as a key player in this. So I'm just trying to a little bit focus here. So this is very much famous, especially the interior permanent magnet, because of the saliency that it gives. Because if you see the inductance of these two paths, that is called D and Q axis. So these two paths giving different inductances and to the flux. So the flux paths are like this. Whereas if you see the surface mount permanent magnet machine, they are pretty close. LD inductance of D and LD inductance of Q is almost same, because permanent magnet permeability is close to air. So it is it sees almost LD equal to LQ. But the real advantage of having this saliency or non equality of LD and LQ gives a additional torque or a surplus torque, that is called say the the two parts, the reluctance torque and the synchronous torque. So the reluctance torque come from the difference between the LD and LQ, and that is where it becomes a more torque density design. So the torque density, if you compare with vis-a-vis induction, this gives a very good say amount of torque as compared to given space, the volume and the weight. So the other thing is the demagnetization of machine. So this is when we use permanent magnets, you can see when we operate machine permanent magnets with this is a simple the you can see here the simple the topology where the permanent magnet is being used differently. So this particular frame outside is a steel, is a high permeable steel, and then there are some coils here where we also demagnetize this magnet, where we also create some field due to the current here. So the demagnetization start happening when we start creating such field. And you can see that when we are operating, so we can correlate this A, B, C, D, all these points are marked here. So when we are operating, especially where this is a machine environment, electric machine environment, where you can see it starts demagnetizing and recoiling on this line. So we have to be very careful that when we should not have very high amount of demagnetizing current to so that it may, because it may demagnetize this magnets permanently. So we may not have magnet or we may have very less strength remaining in the magnetism. So we can also do some studies, simulation to see where the operating point is, how it is behaving. So and the recoil. So maybe we in next few sessions we'll go through these. So this is just to key parameter that I want to touch upon. The another thing is what kind of winding that we should be using, single layer, double layer, concentrated, distributed. There are many options, choices available where you can see the we can see that we have to consider in machine design. The another trending winding is hairpin, where we have better thermal management, manufacturability. Uh, we call that is a winding factor, space factor is much better. The better utilization of space, field factor is much higher, better. So so we call this as a random winding, this type of usual conventional winding, and this is a say hairpin winding. It gives a lot of benefits, but it can be expensive at the same time if we are not having enough volume to handle this. Definitely, the if you see this kind of typical conventional windings, they are wound like this. I mean, they are the three-phase distribution typical. You can see here, they are wound like this, having different topologies like this. Say overlap winding, non-overlap winding, or alternate tooth winding. There are different, say, fractional slot windings are available. We'll run through this, when we should have fractional slot winding, when should have which winding to select, which windings are more appropriate for say particular application. They are all the options, or what I'm trying to project here is all the design space that is available for us. So these are all the parameters that we can play with when we design. So hairpin winding versus all these windings, what we have, conventional winding, we can say, they give us a very good torque density, and they gives very good thermal performance. So they are right now, they are predominantly use research, and where the market is going. As we will see some these also, there is no, I mean, very small volume, or you want to start something, we can definitely switch from this winding to this winding, or back and forth. I mean, we have to redesign those, but definitely thermally, it is better to manage this kind of windings than the random windings. We will also take up this as a topic to for further detailed discussion. The other thing is a harmonic, right? The once we have these all magnets and windings selected, the air gap that we have, the
Then I think,
hello.
sorry, sir. Sorry for the interruption, sir.
No problem. So the harmonic is a very key element, and personally, I would push this as a key element that always we have to consider at various design phases. So these harmonics are either they are coming from the inverter, or they are from the design of electric machine itself. The number of poles we have selected, number of slots we have selected, the winding topology that we have selected, the way we have laid out our permanent magnets, all these geometry elements also plays an important role, because this will reduce our efficiency, reduce our torque, because these are all unintended. So the fundamental is what we are keen. All remaining are what we can say contribute to the losses, and those are very detrimental to the whole electric drive as such, or a vehicle as such, because there will be EMI EMC issues with this. So there are many say bad effects of these harmonics. So we have to reduce all these impacts, or we have to say eliminate few of those. So some winding topologies by nature eliminate some of the harmonics. So the pitching of the winding can eliminate, say, some harmonic. So we will see when we go further, deep dive this session, we will see how uh, the how these elements can be say considered further. So the another element is, I think somebody is asking to, please don't ask me right now the control. Let me use the control. So the the conventional wave winding, and there is some special winding here. So you can see, if you do the FFT on this air gap flux density, you can see there are some harmonics are reduced. If you see, compare these two harmonics here, so different, so the winding patterns will give us reduction or elimination of harmonics, and this is where we will be focusing most of the time in our design. The losses that we any machine has, these are the different say by and large we can categorize in these three to four areas: stator, rotor, friction, windage friction, and some shafts, housings. So mainly copper, and the predominant is copper loss, I square R loss, and the iron loss. So these losses we need to keep in control when we design, and especially when we are using PWM techniques. We have to be very careful what kind of other harmonics are getting injected into the machine, and because those are all again either they are producing negative torque, or they are producing I square R loss, or they are also increasing some iron losses, because iron losses are very much driven by the frequencies that we have. So higher harmonic, higher frequencies, and those losses will get impact. So harmonics are at center stage when we talk about it. So if you see the look at say from if you switch from losses to the efficiency side, it would look like this. So this is where we would be most of the time, the designers or using, what are those people who are using machine, they will be keen to look into this map, efficiency map, that so called. So this is torque, speed, and efficiency. And the challenge is where to optimize this machine in this area. So as I mentioned, whatever the driving cycle, whatever the requirements are there, those will be the those are the elements that we have to consider. So this is the ideal that I have shown, if you remember, and this is something that actually you may get when you test or when you simulate the machine. Uh, the coming to the voltage perspective, like say now here I have considered 400-volt system. You can consider 48-volt system, 60-volt system, whatever, 70-volt system, but there will be one range where it will be operational, fully operational, and there are some voltages, those are the machine won't work, or even inverter won't work. So we call those as a voltage stack up studies. So we have to do those stack up studies where we have to see which component supports the lower voltages, whether machine or inverter or a battery. Voltage range that we have to consider for a machine design. And when we consider machine, when I say machine, it's always a with a regeneration or a generation, right? So the generation element we have to consider. So here we can see that this is a braking torque that machine provides. So we call regenerative braking. And you can see the efficiencies and the torque that we can get through when we. So both sides of machine, that is motoring and generating, is very important. And where when we should, you can see here the regeneration starts in this area motoring is in this area. So these voltages we have to lay down for our requirement, and we have to also say at what voltage level we have to say stop the whole system or give protection to the system. So because in vehicle these voltages will be, because battery is not a constant voltage source as such. Okay, so the voltages will keep on changing with SOC, with your usage of the battery. So we have to see, we have to make this this we have to make sure that at various operating conditions our machine is performing. Then this also constrained by a thermally, so thermal constraint. So what is the incoming coolant temperature? And you can see as the machine starts rolling, it can give very high torque for say 10 seconds. And then as we start increasing our operation, in 90 seconds you can see from 670 volt to 460 newton meter. Sorry, the torque has dropped. So performance is you can see we are moving towards continuous now. So from peak to continuous is now very much thermally constrained. So the thermal consideration is a very key element going from peak to the continuous. Okay, so the the thermal cooling of electric machine is typically done through glycol plus whatever water and glycol combination, and there are separate radiators for say one radiator dedicated maybe for machine and machine and a inverter, or there are different thermal circuits that we can discuss in a deep dive sessions. So the end winding cooling is very important because they are all in air. We have a very high thermal resistance in this area. So how to cool these? Okay, whether we should have some dripping over here, okay, or we should have some shaft cooling that we call, right? So these are all different studies that we have to do: thermal resistances, conductivities, and those governing equations we have to consider. So mostly peak performance is governed by the limitation of peak performance comes from the inverter, because the thermal mass of electric machine is very high. So the what we call the temperature coefficient is much higher for electric machine. So it takes say 1 or 2 minutes to reach to the steady state, whereas inverter will be in seconds. Maybe in 10 seconds it reaches to the peak temperature. So inverter and this machine, we have to consider these thermal constraints together. So you can see here one innovative thermal management introduced by Audi. So you can see what kind of so it's a small animation that you can also Google out and get. This is an open forum, and you can see how they have done the rotor cooling, which is a hot most no, the which is most difficult to cool that area. So they have cooled it nicely. You can see the blue, this area is a rotor, sorry, the stator, this outer, and inside you can see the rotor part. So the coolant goes the how we define the flow of the fluent, and how those are entering, how they exit. So this is one topology they have studied, and they have compared this topology with another improved where they split the entire flow between the stator and the rotor. And the this cooling you can see here, it's a single cooling where the rotor temperature red means very it's still hot, but here you can see the rotor is running now pretty cool, and that is what they call as an innovation there, and that is called say they for eTron they have introduced this recently. Then comes the vibration part, the torque pulsation. There are various sources of vibration, like so let us focus on say machine. So machine gives us a ripple torque, and that ripple torque is something we keep on working. Say in case of induction machine, there are different strategies, but for permanent magnet machine, we give some skew angle to the permanent magnets. You can see here. So these cues will eliminate some of the cogging torque, some of the pulsation in the machine. So they are typically measured in this alpha you have seen here, whatever. So these are the different. So you can see, say 8 piece, 4 piece. So these magnets are arranged in a different slices here.